So I think I'd put off my microphone. And nobody was telling me. When we got into the class, there are some people who said they are not good on the SOMAS code, so I'm posting it again in the chat. So I've posted it. If you didn't have it now, you can use it and join. That's for SMA 210. Now, I need to know if you can see my screen. Can you see the screen?
Yes.
Yes.
Good. I think we stopped here last time.
Yes.
You go up, eh? So we'll move to the next topic. We'll talk about manifolds. Remember, most of our objects are just going to be points in space. So the first definition will be for a basic neighborhood. This will eventually lead us to a definition of a manifold. So we define a neighborhood as follows, or a basic neighborhood first as follows. Let X be an object in space, and then we pick a point P in X. So a basic neighborhood of P is simply all the points of X that are strictly within a distance epsilon of P, where epsilon is greater than 0. So we shall see some examples shortly of basic neighborhoods. Now, a neighborhood of P is a subset that contains a basic neighborhood of P. So a basic neighborhood, a neighborhood does not have to be very, it doesn't have to be circular. It simply has to be any shape, but inside that shape you can find a basic neighborhood of P. So you could cut off any shape around the point P, and that would be a neighborhood, as long as inside that shape you can cut out a basic neighborhood. So we'll have the following remark, that a basic neighborhood must contain the point itself, but it's possible that it may be the only point in the neighborhood. It doesn't have to contain any other point. It can also contain just the point P. This will become clear in the examples. So here is some objects in the plane. The objects are these lines. So the objects are the lines. There are 3 of them. There are these curves. Actually, you see these curves. Those are the 3 objects. And then, in addition to those 3 objects, we have extra points. We have these. You see these 2 points, and then there's 1 more point on this other end. Also, those are part of the object. So the object consists of several components. So the 3 curves and the 3 points. So let's look at them carefully. So if you look at this point P on the end, if you want a neighborhood of P, you need to look for all points that are within a distance, a fixed distance from P. Now the points cannot be outside our set. Our set simply consists of the points on the curve and these 3 isolated points. So if we're looking for any points, we must stick to the points that are in the set. Anything outside the 3 lines and the 3 isolated points is not part of our set. So we measure a distance of epsilon from the point P, and when we cut it out, you can see this highlighted section, the part that is darker, becomes your neighborhood of P. If you consider the point, it becomes your basic neighborhood. If you consider this isolated point, depending on how, if you can stretch out a basic neighborhood. So you look for all points that are within a certain distance epsilon from this point, and they will form some circular area there. Now the that basic neighborhood will consist of this part of this curve these two small parts of the curve. There's this Y, this section that looks like a Y to be inside the basic neighborhood of this point, and so on. So that makes up the basic neighborhood. The other points on the line, the basic neighborhoods for R, in this case, will look like that. And on this other end, we have the basic neighborhood for Q again. So it looks like that. So on this side, there's an example, this point S. So this is an example of a point which is isolated. And if you take a basic neighborhood, there's no other point of the set that is contained other than this point itself. This point is labeled S. I don't know if you can see clearly. I just picked the diagram from the book, but it didn't look so clear in the book. So I hope it's clear. So this point S here, you can find a basic neighborhood of S which contains only S itself and no other point in the set. So this is what neighborhoods would look like in the plane. If you go in the one-dimensional space. Although, yeah, I think we are fine. So here is another example of some neighborhoods. We look at neighborhoods on the cylinder. By cylinder, we mean open cylinder. So it's open on the both sides. And then it's not an infinite cylinder. So it has a finite length, like that. So if you pick a point on the surface of the cylinder, then the basic neighborhood looks like this. It's actually a circular region. The shaded part here. I don't know if you can see the mouse. I'm using the mouse as a pointer. Can you see it? Can you hear me?
Yes, we can hear you, sir.
You can see the mouse?
Yes, we can hear you.
Good. So if you pick a point on the boundary of the cylinder, now the neighborhood will be some semicircular region along with the points on the boundary. So that will be your basic neighborhood. If you pick points which are within a fixed distance from that point on the boundary, then the what do you call it? The basic neighborhood will look like this. Now this other one here is a sphere, the one in the middle, and the neighborhoods here, it doesn't matter which point you pick, all the basic neighborhoods will look like this, will be circular regions. So wherever you go, the basic neighborhoods will just be circular regions. Another thing maybe we should note about the definition of a basic neighborhood, it's strictly within a distance P. So the boundary of that circular region is not included in the basic neighborhood. So they are strictly within a distance epsilon. So less than, the distance should be less than, strictly less than epsilon. So the boundary of the neighborhood will not be included. So this one we have seen. So if you consider the cube, the basic neighborhoods will look different depending on which section of the cube you pick. If you pick one of the sides and pick a point on the interior of the sides, then the basic neighborhood is just this circular region. If you pick a corner point, the basic neighborhood has an interesting look. You can see that. I don't know if it's clear. It wasn't very clear in the book.
Excuse me.
Yes, you're excused.
Is the cylinder open or it is closed?
I said it was open at the beginning.
Oh.
Yes. Try to pay attention. Usilale bwana. Uko na usingizi? Uliamka saa ngapi bwana?
Mapema.
Okay. So it is open. The cylinder is open. So, and for our case, anytime we talk of a cylinder, it will be open. So, I think this one is now self-explanatory. If you pick any point and consider all points that are within a certain distance of that point, certain positive distance, definitely, then you will have different shapes of neighborhood, and you can see the different ones that can occur on the cube and the sphere as well. So these ones are also in three dimensions. So here you have a flap, and you can, on the flap also you'll have different types of neighborhoods. If you pick a point that is on the edge here, you can see the neighborhood is just this semicircular region, including the boundary here, or part of the boundary. If a point is on the surface, on the interior of the surface here, you can see the neighborhood is just a circular region. Now, if it's at the point where this edge meets the surface, because this surface is made up of, say, one strip where this edge is bent and it joins the surface back along this line. So if you pick this point, you can see it has three flaps as part of a neighborhood. Part of a neighborhood is on this side. The other one, you can't see it, it's on the inside. Then the other part of the neighborhood is on this part that is hanging in the air. So it looks like a flap. It has been pulled out on this side, so what you see. This neighborhood for this point looks like what you see here. So this part is the one that rolls on into this other part of the surface. This one rolls on onto this part of the surface. And this one on the outside is what you can see clearly here. So depending on where you pick the point, the boundaries, or rather the basic neighborhoods will look very different. Okay. So we do some definitions here. We define first a one-dimensional manifold. So a set of points is a one-dimensional manifold if every one of its points has a neighborhood that is homeomorphic to an open interval of the real number line. So also a set of points, we can say, we define a two-dimensional manifold next. Here, a two-dimensional manifold is a set of points will be a two-dimensional manifold if each of its points has a neighborhood that is homeomorphic to an open planar disk. So we look at some examples of one-dimensional manifolds. I think someone is trying to join. Let's let them in. Okay. So here we look at some examples of one-dimensional manifolds. So we have an example. The first one we look at is a real number line. So real number line is a one-dimensional manifold because if you pick any point inside any point on the real number line, you can any neighborhood of that point will be some open interval of a real number line. So it will be homeomorphic to an open interval of a real number line, and that is what we saw as a definition. So the neighborhood is homeomorphic to an open interval. That's true for the real number line. An open interval on the real number line is also a one-dimensional manifold, and in a short while we will show that an open interval of a real number line is actually homeomorphic to the whole of a real number line. So if you put together the union of any number of open intervals, you will still end up with a one-dimensional manifold. And it can be shown that any space that is homeomorphic to the unit circle is also a one-dimensional manifold, because the unit circle is also one-dimensional manifold. If you pick any point along the circle, any neighborhood of that point will definitely be like an open interval that is bent, right? So it's just a continuous deformation of an open interval on the real line to fit onto the circle. So that means that any point on the circle definitely has a neighborhood, a basic neighborhood that is homeomorphic to an open interval of the real number line. So these are some of examples of one-dimensional manifolds. So the next one is examples of a two-dimensional manifolds. So the plane itself, the whole of a Cartesian plane is a two-dimensional manifold. Remember again the definition of a two-dimensional manifold. The definition was that it should be have a neighborhood that is homeomorphic to the open planar disk, right? So if you have a point in the plane, you can always find a basic neighborhood of such a point that will be homeomorphic to an open planar disk. You can think of this intuitively. Any open planar disk also in the two space will be a two-dimensional manifold. An open annulus also will be a two-dimensional manifold. We'll draw some of these diagrams and add them before I release a slide so that you can see what this is. Unions of open disks. If you have several open disks, then that is also a two-dimensional manifold. The sphere is a two-dimensional manifold because any point on the sphere, you can always create a basic neighborhood that is homeomorphic to an open planar disk. Because any open planar disk can actually be bent to fit on the circle. The torus, again, is a two-dimensional manifold, and a Klein bottle as well. So the section that I'm going to ask you to read, do some self-reading, will show you how to construct a Klein bottle. I will share the book before the class ends. So in that section, you will learn how to construct the Klein bottle. So that section that you're supposed to read is basically about constructing compact surfaces from plane models. So you will be able to read it and see. So we make some more definitions. Suppose we have a set of points in space. Then we'll say that the set of points is connected if it consists of just one component. So there's only one piece, not more than one piece of it. So that will be connectedness. You will learn about a more rigorous definition of connectedness in topology in fourth year. So we say that X is bounded if there is an upper bound for the distances between pairs of points of X. So what this simply means, if I pick any 2 points in X, the distance between those 2 points will not exceed some number that I know. So for instance, if an example is a circle of radius 2. So let's consider this, a circle of radius 2. If I pick any pair of points inside the circle, the distance between those 2 points cannot be greater than the diameter of the circle. So what is the upper bound for the distance between those 2 points? Can someone tell us? Are you paying attention? Ama mko kwa YouTube? Everyone has gone quiet. So I've asked a question. We are talking about the second definition, this definition which says that X is bounded if there is an upper bound for the distances between pairs of points of X. So what this definition means that I can say that a set is bounded if I pick any pair of points inside that set, the distance between those pair of points will not exceed a given number. So an example is a circle of radius 2, for for instance. And we know that if I pick any pair of points inside the circle, the distance between the pair of points cannot exceed the diameter of the circle. So now the circle is of radius 2. What is the upper bound for the distances between points or pairs of points inside the circle?
4.
4.
Correct. Yeah. So the next one talks about when we say that X is closed. X is closed if it contains all points in the space that are limits of sequences of points in X. So you will learn about this in, if you haven't already, in SMA 206. So you'll get more details on this from SMA 206. So what this means is that if I have a sequence of points in X that converges, if it converges, the limit of that sequence must also be in X. If it is not in X, then my set is not closed. So then the last one is when we say that X is compact. So we say that X is compact if X is both bounded and closed. So if it satisfies these two properties, it is bounded and it is also closed, then we say that the set is compact. So we look at an example here that will take us through this cutout part of the slide, but I think we'll be fine. So the example says prove that the real line is homeomorphic to the open interval -1, 1. So that's the open interval -1, 1. So to prove that two objects in space are homeomorphic, an easy way to do that is to find a homeomorphism between the two. So our task here will be just to find a homeomorphism between the two objects. And the homeomorphism will simply be a continuous function that is bijective, and the inverse is also continuous, right? So we consider this function from the domain will be the open interval, -1, 1. And the range will be the real number line. And this function is hx is equal to tan of pi x over 2. So this is a continuous function. I have not included the graph of this. I think I will include it before I release the slides, so that you can see that it's a continuous function. And it is also bijective. Again, from the graph, you should be able to see. But you know how to draw the graphs. So I think maybe I can give you, you did trigonometry. Ama mkufanya? So try to draw the graph. I will give you 3 or 4 minutes. Try to figure out what the graph of this function looks like. Remember, the domain is from -1 to 1. And the function will be tan pi x over 2. So I'll give you 5 minutes to draw that function. Umemaliza ama bado?
Bado.
So remember the domain is -1 to 1. Not including -1 and 1. It's an open interval. So by now you should have realized that the two lines x is equal to -1 and x is equal to 1 must be asymptotes to this curve, vertical asymptotes. And the curve will pass through 0. And that's all you need to know. So from 0 going towards the right, the curve will be rising. And it will be facing upwards, concave upwards, right? But going towards the asymptote x is equal to 1. It never quite touches the asymptote, but it goes all the way to infinity. And then on the left-hand side, again, there'll be the asymptote x is equal to -1. So from the point 0, the graph will go below the x-axis. And now it will be concave downwards and going towards the asymptote x is equal to -1 and all the way to infinity. But it doesn't touch the asymptote. Another thing you need to learn is if you have some of you may have these graphing calculators. When you have this kind of thing, you can put it in the graphic calculator. But it's important also that you understand the function itself. So if you follow my description, you will see that it is a continuous function. It doesn't have any breaks in between. And then it is also injective and surjective, and therefore it's a bijection. And that means we can find the inverse of this function. So I need you to, have you finished drawing the function?
Yes, we are finished.
After I have told you.
No, we have done calculations.
Okay, that's good. If you have managed, that's perfect.
Yeah.
But I will include the drawing before I release the notes. You can compare what I draw and what you will have drawn. So now, since the function is bijective, we can find its inverse. Can you confirm that this is actually the inverse? Now I'll give you another 3 minutes to find the inverse of this function and confirm that it is exactly the same as what I have on the screen. You know how to find the inverse of a function?
Yes.
Yes, we know.
Okay, then find the inverse of this function and confirm that it's exactly the same as what I have on the screen.
Yeah, it is the same, sir.
Correct. So now you have the inverse. Now you do. Are you able to draw the inverse? So another way of drawing the inverse is just to reflect the curve of the function of h of x along the line y is equal to x. Then you'll find the graph. You will also notice that the domain of the graph now will be the real number line, the whole of the real number line, and the range now will move to will now be the open interval negative 1 1, right? So again, this inverse is continuous, and it's a bijection, and that means that this function is a homeomorphism from negative 1, this open interval negative 1 1 to the real number line. So we've been able to find a homeomorphism between these two objects, the real number line and this open interval negative 1 1. So what that means is that the two objects are homeomorphic and therefore topologically equivalent. So this open interval negative 1 1 and the real number line are homeomorphic. So for a topologist, you can hear me?
Yes.
Yes.
Okay, that's good. So for a topologist, there's no difference between an open interval and the real number line. They are the same thing because you can find a homeomorphism between the two. So that means if you have an open interval, you can stretch it and as far as you can to form the real number line. If you stretch it infinitely, and that applies to any open interval. Any open interval on the real number line will be homeomorphic to the one-dimensional space, and that is just the real number line. So that's the conclusion we can make on that. Now we want to make a connection between homeomorphisms and these four properties that we listed here: the connectedness, boundedness, being closed, and being compact. So what is the connection between homeomorphisms and these properties? So we make the following observations. The real number line is closed because if you have a sequence of points of real numbers which converges, it will converge to a real number as well. So any convergent sequence of real numbers will converge to a real number, and that is the definition of being closed. But it's not bounded because there's no upper bound between the distances, for the distances between pairs of points on the real number line. Right? There's no upper bound. So the real number line is not bounded. On the other hand, the open interval from negative 1 to 1 is bounded because there's an upper bound for the distance between pairs of points in that interval. What is the upper bound for this open interval? What is the largest distance between any pair of points in this open interval from negative 1 to 1? So if you, pardon, 2. Okay. Yes. That's perfect. So that confirms that it is bounded, but it is not closed because it's possible to find a sequence of points in this interval that converges to 1, yet 1 itself is not 1 is not in the interval. 1 is not part of that interval, yet you can find a sequence of points inside the set which converges to 1. So for an example is a sequence of points which take the form n over n plus 1, where n runs from 0 to 1 to 2 and so on. That sequence will converge to 1, and n over n plus 1 is a point. It will be points inside this interval. Yes, they will converge to a number that is not in the set. So this is not closed. So the example I've given is the sequence n over n plus 1. The other thing we can notice here is that none of the two objects are compact, because if you look at the real number line, it is closed but not bounded. For it to be compact, it must be both closed and bounded. If you look at the open interval from -1 to 1, it is just bounded but not closed. So again, it is not compact. So that maybe suggests something that compactness must be preserved, and we shall see that later by a homeomorphism. So the other thing we can observe is that both objects are connected. They are both made up of just one component. The real number line is just one piece. The open interval from -1 to 1 is just one component as well. So both of them are connectedness. So we can make a guess that homeomorphisms must preserve connectedness and also compactness. The homeomorphism does not necessarily preserve the property of being bounded, because you have two objects. One is bounded and the other one is not bounded, but they're still homeomorphic. But if you have a homeomorphism between two sets of points in space, then if the first set is connected, the second one must also be connected. The same with the case if the first set is compact, the second set must also be compact, and vice versa. If it is not compact, the second set will not be compact as well. So here's some examples of two-dimensional space. It says the open unit disk is homeomorphic to the two-dimensional space. Now here, I did not construct the homeomorphism between the two sets, and I have given you the task to do that. So you try to construct a homeomorphism between the two space and an open unit disk. What is important now is you need to have a pen and paper so that you take note of some of the tasks that you've been assigned. Although this one is already in the slides, if you get the slides, you can still read it there. You've been asked to construct a homeomorphism between the two space and the open unit disk. Now that homeomorphism will confirm that the two sets of points are homeomorphic. So the second example of a two-dimensional space is an open disk. No, an observation rather. The observation we can make about this is that both sets are connected. Now the two space is closed, but it's not bounded again. The two space is just the plane. The plane is not bounded. You can go as far as you wish in the plane, but any set of points, sequence of points in the two space, if it converges, it will converge to a point in the two space, but it's definitely not bounded. So you can see again the homeomorphism does not care whether both are bounded or one is bounded and the other is not. That is not really a big problem for the homeomorphism. And the same ideas from the other end. So another example is a unit sphere is a compact and connected two-dimensional manifold. And we had shown earlier that it is homeomorphic to the surface of a cube. We constructed that earlier. I will not go back. It's in the slides on the previous video. If you need to review that, it's available. So for two sets of points, here is a theorem now, which we already talked about this, but we're just making it formal. If you have two sets of points in space, x and y, that are homeomorphic, then if x is connected, y must also be connected. And if x is compact, y must also be compact. We talk of a curve this is a definition. So a curve is basically a connected one-dimensional manifold. As long as it's a one-dimensional manifold and it's connected, we shall call it a curve. So here's a theorem. The theorem says any compact curve is homeomorphic to the unit circle. We shall not, some of these theorems we will not prove, but it's information that you need to carry along with you as we move along. So it says any compact curve is homeomorphic to the unit circle, and any non-compact curve will be homeomorphic to the real number line. So if a curve is homeomorphic to the real number line, it will not be compact. The reason for that is homeomorphism will preserve compactness, and also if you have two sets of objects that are homeomorphic, if one is not compact, the second one will not be compact. And if one is compact, the second one must be compact as well. So now we define a surface. A surface is a connected two-dimensional manifold. Previously, we just defined the two-dimensional manifold, but now a surface is a special case of a two-dimensional manifold, which and what makes it special is that it's connected. So if you have a two-dimensional manifold that is connected, then we call it a surface. So here are some examples of one is a circular paraboloid defined by the equation z is equal to x squared plus y squared. Now this is a connected two-dimensional manifold. I don't know if you have learned how you did geometry, so you must have learned how to draw these things.
Yes, we learned about this. The dimensional.
Okay. So the hyperboloid, the second example, the hyperboloid z squared is equal to x squared plus y squared plus 1 is not a surface because it is not connected. It is a two-dimensional manifold, yes, but it is not. We cannot call it a surface because a surface is required to be connected. So for the better part of this course, we shall focus on compact surfaces. So these are the drawings for these objects. So the first one is the circular paraboloid, and the circular paraboloid appears here. It's this first diagram here. Now this has been chopped off. Circular paraboloid goes all the way to infinity. So since we can't draw to infinity, it has been chopped off at this point. So this is not a complete circular paraboloid. It's supposed to go up all the way to infinity. And it's you can see it's only one component, so it is not it is a surface. But the hyperboloid consists of two sheets, so they are not connected. These two are not connected. It has two components, and therefore it's not connected. It is a definitely two-dimensional manifold, because if you pick any point on this surface, you can always find an open a neighborhood which is homeomorphic to the open planar disk, to an open planar disk rather. So this second diagram shows the hyperboloid. I think we have two. This z squared is equal to x squared plus y squared plus 1, and that, since it is not connected, we say it is not a surface. So I think we shall stop around here. So definition, a compact surface is said to be non-orientable if it contains a subset that is homeomorphic with the Mobius band. If it doesn't have any subset that is homeomorphic to the Mobius band, then we say it is orientable. So a non-orientable surface is basically a surface that has only one side. It is one-sided. So if you can move around the whole surface without having to pass through. So for example, a cylinder is orientable because, or rather, a sphere is orientable because if you want to go to the other side of the sphere, the inside of a sphere, you have to puncture it to go to the inside. So it's two-sided. But a Mobius band or a Mobius strip is not two-sided because I can move along. It doesn't have two sides. It just has one side. So I can move along the whole surface without having to punch any holes through it. So a non-orientable surface is basically a one-sided. It has only one side. But an orientable surface has two sides. So that's the simplest way to think of it. It can be done in a more rigorous way, but that's the simplest way to think of it. Now, the rest of the stuff we needed to do requires your knowledge of the plane models. So that is the assignment, reading assignment I want to give you. So I will just stop this display and now share the pages in the book that I want you to look at. So let me present again. So this is the book that we'll be using. It's called Topology of Surfaces, Knots and Manifolds, first undergraduate course. Now there are some sections in the book that I want you to read, and those are the ones involving the construction of I think it's 1.6. What is it? Yeah, 1.4. Starting from 1.4, this section, constructing objects from plane models, starts from page 18 and up. It's just 4 pages, so it will take you less than the time it takes you to watch Arsenal losing. So from 18 to 22, and I think you still have about 1 hour remaining. You can use that time to cover this section and read it carefully because we shall be using that information later. I will not cover that in class, so you'll have to read it yourself. It's only 4 pages. I will share the book shortly. So if you go to the, we did this in class, so what we haven't done is we did this as well. So what is left for you to do, and also some of the stuff we have already done is in this book. So if it didn't make sense, you can read it with more detail in the book. So, okay, more and more. Yeah, this is a section. So you need to show constructing objects from plane models. So here are 2 plane models, one for the cylinder and one for the Mobius band. Read it very carefully so that you understand what these 2 arrows represent. Why in this case, for the cylinder, the arrows are both facing the same direction. For the Mobius band, the arrows are facing in opposite directions. You need to, the next one is a construction of a torus. So that's a plane model. Again, pay attention to the arrows. The arrows are really important in this. Then there's a construction of the sphere from the plane model. Again, pay attention to the arrows, and you will see that these arrows for the sphere point in slightly different directions than the arrows from the torus. Then there's this one for the Klein bottle. This one is a very interesting construction because it's actually it's a 2-dimensional surface, but it has, if you want, and its natural space is a 4-dimensional space. Now, but if you want to construct it in 2-dimensional space, it will intersect itself. But again, it is a one-sided surface. There's a nice video on YouTube. I'll look it up, which explains why this is a one-sided surface. So this is a non-orientable surface. It's one-sided. There's also one more for the projective plane, but I think that will come later. So you need to read the whole of this section. You need to read the whole of this section and section 1.4. And we shall be using that for the future classes. So what I can do is I need to give you the link to this. So I'll stop sharing now, then I can put it on the cloud. So I don't need to continue recording now. I can stop the recording.